Stripping down science. The Naked Scientists.
Hello and welcome to this special pre-recorded edition of The Naked Scientists with me, Mira Senthilingam.
And me, Dave Ansell.
This week we're looking back at the year's highlights from the world of engineering.
Over the past year, Mira and I have roamed the UK meeting engineers and scientists from across the country who are working on great pieces of engineering, both old and new, to bring us some of the technologies of the future.
So this week we bring you the best of what our travels have found, including turbines that harness energy from our rivers and the technology allowing mining companies to purify minerals such as copper from the millions of tonnes of ore mined each year.
Plus the equipment that allows pharmaceutical companies to make billions of drug tablets with precise chemical components on a daily basis. And we go back thousands of years to an ancient form of engineering still in use today, ironworking or blacksmithing, to bring you the science behind this ancient craft.
The oranger it is, the softer it goes. Now when I hammer it, it's going to be easier to handle.
Iron's got this really unique property that at about 700 Celsius it transforms from being one crystal structure to another. So just using the skill of a blacksmith, Gordon's managed to control the atomic structure of a piece of iron. Really amazing skills.
Plus, we've got a special new engineering insight for this week, looking into the design of the famous Dam Busters bouncing bomb.
Then we had to design how to fit it underneath a plane. We had to design how to make it spin, and that was one of the things that Barnes Wallis found was really important, that this thing had to spin. And we had to figure out how to release it at the right time, at the right height. And actually we had to make ourselves a target. Barnes Wallis had Nazi dams as the target. Well, we built our own dams.
So a wide range of technology coming your way as we bring you the best of the last year in engineering.
The Naked Scientists podcast is powered by UK Fast, the UK's best hosting provider. On the web at ukfast.co.uk.
This is a special pre-recorded edition of The Naked Scientists with Mira Senthilingam and Dave Ansell. And this week we're looking back at the year's highlights from the field of engineering.
And we'll start with a beautifully simple piece of engineering that many of us will have come across on roads and motorways across the country, the cat's eye. This is a lovely story of biomimetics, and its origin is a classic tale of taking observation made whilst driving along a foggy road and turning it into a life-saving invention.
And we found out exactly how these cat's eyes work when we went along to meet Hugh Hunt at his office in Trinity College at the University of Cambridge. An office filled with all sorts of gadgets, including a wide variety of mirrors. Mirrors which Hugh then used to explain just how cat's eyes use the light from our car headlights to guide us on our way.
Well, we know, for instance, that the headlights from the car are very bright. So I've got a little torch here, and if I stare straight into it, it's very dazzling. And if I have a mirror, I can reflect the light into my eyes, and it's also very dazzling.
The light's just coming straight back at you.
Coming straight back. And if I have a piece of white paper, well, it's not at all dazzling.
I guess a normal mirror will shine light straight back at you, but as soon as you get the angle slightly wrong, that beam is going to miss your face and it's not going to look very bright at all.
So the challenge there then is designing something that can catch light from many angles and still make it visible back at you.
Exactly right, Mira. And now, one thing you might have noticed, if you've ever been into a bathroom where there's two mirrors side by side at right angles to each other, it's quite interesting to look at what happens. So I've got a couple of mirrors here, and just at right angles to each other. Now, Mira, if you look into the mirror, you will see that your reflection is at the intersection of the two mirrors.
Yeah, my face is basically, I can see myself at the intersection, at the joint.
Now, what's really interesting is if you move your head from left to right, your reflection will always be at that intersection.
That's right, it's not moving.
And it's almost as if you've got a perfect plane mirror, which is always pointing at you. It compensates for the motion. Wherever you're looking from, it always reflects directly back at you. Now, if you take a light, I've got a little torch here, and you hold that by your eye, you'll find that all rays reflects directly back at you.
Yes, it was coming straight back at my eyes, actually. It's hurting a little bit.
And so this is the basic principle of what's called a retroreflector. It reflects directly back at you. And it works because if you do the angles of reflection on the two mirrors, when you add up the two sets of reflections, the total angle of reflection is always 180 degrees. So whichever direction the light goes into this pair of mirrors, it comes back at 180 degrees.
So this works great if you're moving left to right, but at the moment if you move up and down, your image moves, so it's not going to work very well like that. How do we get around that problem?
The next clever trick is to have 3 mirrors at right angles. So imagine you go into your bathroom and you've got one mirror on the floor and 2 mirrors at right angles on the walls.
Which you've now constructed here.
Constructed. Well, where do you see your reflection now, mirror? Is it?
It's at the intersection, but of where all the 3 mirrors meet.
Right. Now you take the torch and you put that by your eyes, and you should find.
Oh, it's glaring back at me.
And as you move left, right, up, down, any direction.
The light is just chasing me.
Always. It's spooky.
So whereabouts are these retroreflectors used then?
Well, they're used in all sorts of applications. So perhaps some of the common ones that we're most familiar with are reflective clothing, reflectors on the side of the road, and even reflectors on your bicycle. They are retroreflectors. And they all work, generally speaking, on the principle of this corner cube idea, the 3 mirrors at right angles. And in fact, it's called a corner cube.
So that is quite a wide range of uses, really. But Dave, another use of them that's quite commonly known is cat's eyes that we see dividing lanes in the road for us to see lane markings and essentially see when we're driving on busy roads at night.
That's right. In the 30s, there was a guy called Percy Shaw who was driving along the road and suddenly discovered it's really, really hard to follow the road in the mist, in the dark. And then he saw some cats, and their eyes were shining back really brightly. If you ever shined a torch at a cat, you see their eyes reflecting incredibly brightly.
This is because they have reflectors essentially at the backs of their eyes.
Yeah, their eyes act as retroreflectors. So we attempted to copy these and put them in the road.
We have some of these cat's eyes here with us. So how do these actually work, Hugh?
They work by taking the light coming out of our headlights and shining it directly back at us. And there's some really neat things about the design of these cat's eyes. Firstly, of course, they're optically very good and they reflect the light back. But what would happen if they got covered in mud or grit and stuff from the road? Well, one of the really lovely things about this particular design is that every time you drive over them, there's a little rubber flap at the front, a bit like eyelashes, really. And the very action of driving over these things
pushes down.
The cat's eyes down and clears the mud off them. And it's just such a beautiful piece of clever engineering. Because, of course, this has to be designed so that over the lifetime of these cat's eyes, you've got several million lorries passing over. They've got to survive cold winters, snow ploughs. They've got to survive hot summers.
So do these cat's eyes follow the main principles we've been talking about then with corner cubes?
Well, there are different types of cat's eyes. The ones that were developed in the 30s are actually more like a combination of lenses, and in fact operate much more in the way a cat's eye actually works.
Yeah, that's right. If a cat's looking at something bright like a torch, the light from the torch will get focused onto its retina, so it gets an image of the torch. But the cat's eye's got a reflecting membrane at the back of the eye, which reflects the light straight back the way it came out through the lens, which focuses the light exactly straight back towards the torch, which was putting the light out in the first place.
It's really a very nice little bit of geometry and looking at how you can design a lens and a mirror, curved lenses, such that you get the light to come straight back out the way it came in. But it's much cheaper and much easier to make a corner cube idea. You can just press them out of a piece of plastic, make cheap reflectors for your bikes. And those sorts of reflectors are used on the posts on the side of the road. They're not driven over, and they don't get covered in mud and grit from the surface of the road. They're just much more like bike reflectors that are stuck onto the posts.
You sometimes get them stuck onto the road, but they tend to be the ones which fall off within a couple of years.
But also, along the motorways and things, you see different colours of these cat's eyes to mark out, say, the hard shoulder and things like that. How do these work?
It's just coloured plastic or coloured glass. So in the same way as if you shine a light through a piece of red plastic, the light turns red. So if you make the plastic is coloured red, it'll be red.
So there are just such a wide range of uses for the concept of just reflection.
Well, it's wonderful. It's one of these things that if you actually stop and think about how they work, it's not obvious. When you find out how they work, it's just fantastic to understand it.
Incredible. Just some basic principles of physics used to help us see quite clearly at night time. That was Professor Hugh Hunt from the University of Cambridge. And Hugh will be back later in the show with an insight into his recent work engineering a replica of the famous Dam Busters bouncing bomb.
From protons to photons and gluons to muons, The Naked Scientists. Science that's fundamentally more fun.
This is a special edition of The Naked Scientists with Mira Santhalingam and Dave Ansell. This week we're exploring some of the best bits of engineering we've come across in the past year.
One area of science many of us hear about on a daily basis is climate change. Academic institutions and companies across the globe are desperately trying to come up with ways to reduce carbon emissions, or even better, to provide an alternative source of energy. And we came across a great idea back in December, didn't we, Dave?
Yes, it was a fascinating small company called Green Tide Turbines, and they had a nice idea to use turbines to harness the energy from tides around Britain. But whilst they're still developing that, they are now using the same technology somewhere altogether more exotic.
Dave and I went out to their very cold riverside testing site in Cambridgeshire. I remember it had been snowing the night before and my fingers felt like they might drop off, but it was really worth it to see these turbines in action and find out a little more about how they work, with the CEO of Green Tide Turbines, Michael Evans.
If we're talking about a tidal turbine, we're developing technologies that have to survive some of the most aggressive environments in the whole planet. We've got heavy moving water, which contains huge amounts of energy, often in very remote locations, which are very hard to access because obviously you've got these very strong tidal currents and also some extremely large forces, which is the whole reason why we want to put turbines there, to tap some of that. So the emphasis really needs to be on devices that are really, really simple, very easy to maintain, very robust, and also quite cheap.
I guess the default thing to do would be to take a known technology, like take a wind turbine and stuff it underwater.
Absolutely. A lot of our competitors have followed that very, very philosophy. Basically, they've just got wind turbines with shorter blades that are made to be waterproof, and they dump them under the sea. And the sea just isn't water. There's lots of stuff that it carries in it. Things like fishing nets, even submerged containers that have been washed off ships, for instance. These all sort of find their way into these fast-moving flows of water and are basically flung at these devices. So you've got these wind turbines with their delicate blades spinning around in this sort of flow regime. When these things get hit by these objects, they're not going to survive particularly well.
To tell us more about how the Green Tide turbine design approaches these challenges is Tom Clark, who's the research director.
Well, we have a different kind of concept, which is moving away from the wind turbines underneath the sea. What we do is we put much smaller rotors inside a duct, which allows us to capture a similar amount of energy, but using a much smaller and more robust rotor.
I guess the first thing I'd say, if you've got a very small rotor and you're sort of squirting lots of water past it, surely everything's moving very fast. This turbine should be spinning very quickly and kind of mash anything which it hits.
That's right, but what we've been able to do, Dave, is use both a stator and a rotor. So a stator is essentially like a rotating turbine, but fixed in position. What that does is it causes a swirl of fluid inside the duct, and then the rotor takes out that swirl and generates energy by doing so. So, although the rotor is moving fairly fast, it's not moving as quickly as perhaps a design without a stator.
So you're regulating really the flow of water approaching the rotor?
That's right. That has the additional benefit, actually, that any turbulence and gustiness in the incoming stream is actually straightened and aligned as well. A lot of people don't realise it, but the tides don't move just uniformly. There's a lot of turbulence, swirling eddies and so on, and currents, which upset the behaviour of turbines in the current. Benefit of our design really is that you can actually stack our turbines closer together in a tidal farm than with open type turbine designs.
So your system's causing the water to spin, and then you're changing the direction of that spinning water completely using your rotor. So because you change the direction a lot, you don't need to be moving the rotor as quickly.
That's right, yes. Because we have a swirling motion in the inside of our duct, our rotor can be moving much more slowly. Effectively, it moves with the water. So there's less of a relative speed between the water and the rotor. So it's much less damaging for fish, and it's much less likely to get debris and other objects caught in the flow through the turbine.
Well, now you mentioned that they can be situated quite close to each other, but what are the actual dimensions of the turbines?
Our tidal turbines are in general in the range of 10 to 15 metres in outside diameter. But the ducts are quite big, so the rotors are actually substantially smaller than that, of the order 6 metres.
We're at one of your test sites now. We're just alongside a river, and you've got a tunnel through which water's flowing through. It's about 1.5 metres to 2 metres wide, and you've got one of your turbines just placed in the middle. It's about 1 foot wide in diameter. Tell me a bit more about how this setup works, though.
Well, it's called a Venturi arrangement. Essentially, there's a nozzle which accelerates flow into our turbine for the purposes of testing, because we need a higher flow rate to accurately test the turbine. So the flow rates that we reach in the test section of our water tunnel are around about 2 metres per second. The action of the duct around the turbine actually accelerates fluid through the turbine disc, which means that the velocity inside the duct is slightly higher than the mean flow rate. It's about 2.5 or 3 metres per second. We have part of the flow of a river diverted through our test facility. We can control the facility, we can control the flow rate of the river using a sluice gate up in front of our turbine.
Can we see it in action then?
You certainly can. All we need to do is open up the sluice gates.
Right, so the sluice gates are open and the water is now just flooding through.
That's right. Well, flowing through the tunnel is about 3 cubic metres per second of water. We've got water travelling up to 2 metres per second.
Going through then the turbine, how much power will be being generated here?
Well, that corresponds to a power of about 500 watts, which really isn't very much. That's about half a household kettle. But I should say that it's a very, very small model that we're using. The energy capture scales up dramatically as you increase the diameter up to our tidal turbine scale. Our commercial scale turbines typically produce around 1 megawatt of power, which is useful. I think that generates enough power for about 300 homes.
Having seen it in action then now, moving back to you, Michael, where is it hoped these turbines will be used? What are the upcoming projects then?
Well, we've had a great deal of interest from developing countries where there's lots of rural communities well away from established infrastructure needing power, and relatively small amounts of power, generating power for lighting, for running mobile communication systems and things like that. One country in particular who's very keen on our technology is Brazil. So these will be on a scale of about 1 metre in diameter, installed in probably in northern Amazon region initially. They'll be generating around about 5 kilowatts of energy.
I guess even if you're going to put diesel generators up there, you still have to ship the diesel up there regularly, so it's even less hassle than that.
Absolutely, and on top of that, you've got a lot of enthusiasm for clean technologies, and other alternatives such as photovoltaics and wind wouldn't really work in a rainforest type environment where obviously you've got lots of clouds most of the day, and also with the trees there's not very much wind at a usable sort of level. So a river generation technology is ideal for this sort of environment.
So although you started off building a tidal turbine, you've ended up putting it in rivers instead.
Making smaller turbines is a lot cheaper, obviously, and we need to prove our technology. The river turbine is a fantastic test bed to actually develop the technology.
Michael Evans, and before that Tom Clark from Greentide Turbines. They really were impressive things to see once they got going, as they can produce such a large amount of power when at full scale.
Yes, but what I found the most fascinating was the way they developed an idea to produce tidal power, but it's first going to be used thousands of miles away in a river. In fact, Greentide Turbines have just signed an agreement to collaborate with the Federal University of Rio de Janeiro to develop the turbines for use along the Amazon River in Brazil. And now they're in the process of setting up a company there to manufacture and distribute them. But now moving away from renewables and over to an industry that uses a large amount of energy for drilling, digging and extracting millions of tons of mineral ores from the earth on numerous sites around the globe. You guessed it, the mining industry.
Now, Dave, before we explored this area, I mainly just thought of mining to involve multiple trucks and diggers essentially finding sources of ores and just simply digging them up. I hadn't really thought about the incredible science and engineering needed to actually purify those ores and get the mineral that you're looking for.
That's right. The process of extracting the minerals is very, very difficult, especially doing this on an immense scale like the gigantic copper mines you see in countries like Chile. As the Imperial College engineer Jan Siliers explained.
I think maybe we should take a step back, just look at the scale of the mines we're dealing with nowadays. The copper mines we're talking about treat literally tens of millions of tons of rock a year to produce hundreds of thousands of tons of copper. But within the mine, maybe only 2% of the rock we mine is valuable mineral and the other 98% is waste. And in order to do the separation between the valuable minerals and the waste minerals, we need to grind them very finely down to, let's say, less than a tenth of a millimeter approximately before we can do the separation. This is called liberation. And once we've ground up the rocks and they're liberated from each other now, we actually want to do the separation from the valuable minerals to the non-valuable ones. The workhorse of mineral processing nowadays, where we have to separate out these very small amounts of minerals from each other, is a technique called froth flotation, which depends on the hydrophobicity differences between different minerals. In this case, we make the one mineral we do want hydrophobic, meaning water-hating, blow air through this mixture, a slurry or almost a mud of the mixture of minerals. The hydrophobic particles stick to the bubbles, float to the surface, and form a continuously overflowing froth that contains all our valuable minerals.
So are the valuable minerals chemically different so your additive can make them hydrophobic?
They have to be, and in this case, nature's made it so that the valuable minerals are sulfide minerals. They are copper iron sulfides or copper sulfides, something like a chalcopyrite as it's called, versus an oxide mineral, which is our gangue or our waste minerals. The other 98% is that. And so it's quite relatively straightforward for this chemical to attack the one mineral versus the other one and make it hydrophobic, whereas it ignores the other ones and leaves them hydrophilic, water-loving.
So what types of minerals is this process used to extract?
Pretty much all the base metals, copper, lead, zinc primarily, and many of the other metals are associated with the base metals. So platinum comes up as a nickel, copper type deposit. Silver often comes with lead. And all the major gold mines in the world now, the gold is actually a byproduct of the copper production.
What's the scale of this process industrially?
At the moment, the flotation process for copper accounts for about 70% of the world's production. If you look at a typical mine in North America or in Chile, where the massive copper mines are nowadays, a typical mine would maybe treat 10,000 tons of rock an hour. That's a cube of rock 15 meters by 15 meters by 15 meters every single hour. So the scale and the tonnage is just unimaginably large.
And the tanks themselves then that the rock is in and the bubbles are being pushed through?
The biggest tanks nowadays are 300 to 400 cubic meters each, and a typical mine would have 60 to 70 of these tanks in a row. So yes, we're talking about aircraft hangars of froth.
This process has been used for about 100 years now. So, I mean, we're in your lab where you study the foam and flotation process. What aspects of this are you studying to further it or enhance it?
We've been looking at the physics of the froth, the bubble size, the velocity at which it flows, and what variables affect that.
We've got a large kind of water bucket / tank in front of us with a gutter around it, with many tubes going in, many tubes coming out, laser monitors on top as well as cameras attached. So I imagine you initiate a foam here, but what are you actually monitoring and how?
Yes, as you see, the tank is containing our slurry. The froth is forming inside that and overflowing the edge into what you call the gutter, we call the launder, and then overflows into a recirculation tank and through the pump, as you can see. What we're measuring is two things. The one is the height of the foam overflowing the edge of the tank, and the velocity, which we measure with a video camera you can see in the back there. We are trying to measure the volume of the froth overflowing. So we need a velocity, we need a height, and of course we know what the length of the lip is. And that, if we multiply those three together, we get the volume of the froth.
I guess the depth at which the froth is overflowing is quite important, because if it hasn't had time to separate out and you're sort of pumping froth through too quickly, you're going to get lots of other minerals mixed in. And if you go too slowly, you're just not going to get enough production from your system.
What we've discovered over our years of research is that the rate at which the bubbles are bursting on the top surface is the critical parameter for controlling this process.
So if the bubbles are bursting, you're essentially losing the separation which the bubbles have done already for you.
If there's too much bursting, we lose the mineral we want. If there's too little bursting, we collect too much of the minerals we don't want. And it's that delicate balance that we're trying to optimize here. The main variable to control the rate of bursting is how much air we put into the tank.
Is this something that's controlled and monitored on industrial mines at the moment?
In some mines it is. It's not necessarily controlled, although there's move towards that. We'd like to see that implemented far more widely, and that this technique of monitoring the volume of froth overflowing is used as a control measure. If you look at a typical copper mine, we recover about 90% of the minerals that come into our process, and we lose about 10%. If we push that to 91%, that extra percent is worth, say, $20 million per annum. So there's a big incentive for us to get this right.
Jan Cilliers, Professor of Minerals Processing at Imperial College London. Now, Jan showed us images of the mines where this froth technique is used, and their scales and sizes were just incredible. I mean, they treat 10,000 tonnes of rock an hour.
It was incredible, but the thing which really got me about this interview was just one number. That's that 5% of all the world's energy use goes into crushing rock, which is an astronomical figure when you consider that it's almost entirely for extracting metals like copper, which goes to show just how important they are for our everyday life. And you can see videos of this and all the engineering topics discussed this week online at nakedscientist.com/engineering.
Distilling the best science. The Naked Scientists.
You're listening to a special pre-recorded edition of The Naked Scientists. And this week, we're bringing you some of the best bits of technology from the world of engineering.
And now we go back to one of my favourite pieces of engineering that we explored this year, shape-changing or bistable structures. These, as you may have guessed, are structures that can completely change shape and switch from one form to another and back again.
This is an area Dr. Keith Seffen from the University of Cambridge explained to us, using nothing more than, well, a snap bracelet.
As you can see, it's got a little bit of plastic covering on it, but it's predominantly straight, or it is straight in one configuration, and if you flick it against your arm, it'll wrap around it and adopt a circular shape.
This has got sort of two configurations, one of it where it looks straight, but if you look carefully at it, it's curved in the other direction, just very slightly. And the second one's when you wrap it around your wrist, and it's essentially just a straight coil in one direction.
That's right, Dave. If you take it apart, if you remove the plastic sheath, it looks like a tape measure. Straight in one configuration, but curved gently across its width, and in the other configuration, wrapped up a bit like a tape measure sitting inside a cassette spool.
So, I mean, this is something many of us have seen, but how does it actually work? How is it possible for it to have these two configurations?
Well, your ordinary tape measure won't have this. It will just want to be straight. What you have to do is manipulate it, create or embed, if you like, the second shape, the desire to be curved.
So you're basically just distorting the metal itself, plastically deforming the tape.
What you can do, if you can get hold of a length of tape, is to cut a length, wrap it into a coil, wrap it around a pencil perhaps or your finger, and try and pull it as tightly as possible. And what that does is to permanently deform the tape measure into the circular position. It likes to be in that shape, but if you then pull it straight, it will prefer to be in that shape as well. And that creates, if you like, this bistable property where it desires to be in both configurations at once.
So you've now rolled up this tape measure quite tightly around your finger and opened it back up. So now with just certain pressures or just pushing on certain points, it should just flick.
That's right. If you just take it and push in the middle, as you can see and hear, it sort of pops into the cylindrical configuration or the wraparound configuration. And then you have to physically unravel it to create the straight structure again. What you need, however, is two very different shapes for this to work. And in the case of a tape measure, it's long across its length but curved across its width. And that changes when you wrap it around your finger, when you wrap it around a pencil. It becomes flat across its width and coiled along its length. And it's that antagonism, if you like, that permits the properties that you see. And the shapes are so different that to physically move from one to the next, you have to come along and break it with your finger or push it in the right place.
Can this also be used in other types of materials as well?
Sure thing. We have different engineering materials. A popular lightweight structural material is carbon fibre. And we work closely with a company that make tubes from carbon fibre that have the same bistable property. And I've got an example here of one where we've actually tuned the properties so that it prefers both to be straight and to be coiled at the same time whilst you're holding it. And we call that a neutrally stable structure.
So it's not snapping between one to the other, it's just moving very gently.
That's right. In the previous structures, there is a desire to be in both shapes at the same time. They can only occupy one shape at a given time, whereas this one can occupy both. And it occupies both by having part of it straight and part of it coiled and a kind of funny transition region in between.
I guess this is a really neat way of storing a very, very long tube. If you want a long tube for something, you can just roll it up the other way and it turns into a short, fat, easily storable object.
And in addition, because it's quite happy to be extended to any length, you can have a tube of any length. And for that reason, imagine you wanted to have some kind of device that would enable you to look into buildings at a particular height. So what you can do is extend the tube, have a camera on the top of it, and then look into, say, the window of a burning building if you're a fireman or whatever. But you don't want to be carrying this around in the extended configuration, so you'd roll it up, stick it in your backpack, it'd quite happily fit there because it's coiled and neatly packed.
Is there anything else we can also use these structures for?
Well, what these little demonstrations have shown you is that crucial to the performance of these is what you start off with as a basic shape. With the snap bracelet, what we thought of doing was taking several of them and linking them together to produce something which was a bit wider, rather than having just a single strip, several strips next to one another. And then we had the idea of alternating those strips. And what you end up with then is something that looks a bit like a corrugated sheet. And like a flick bracelet where we're able to give it pre-stress, we can make the corrugated sheet, which is nominally flat, coil up into a cylinder.
So this is actually a really quite a nice design. Basically, it's a whole series of these tape measures next to each other, but one upside down, one the right way up, one upside down, one the right way up. But instead of separate tape measures, it's all just made out of a single sheet of metal, which has just been bent. And this means that because it's actually got some depth, it's actually reasonably rigid as a flat sheet. But if you bend them beyond that point, it just starts to roll up into a tube about 2 inches in diameter. And now it's still quite a solid structure, but it's rolled up and takes up much less space.
But what this demonstrates is a very simple mock-up of an application of our technology where you might want to give some support to a very flexible, thin electronic display. There are people out there in the electronics industry trying to make displays as thin as possible to give them this nice flexible feature. Electronic ink, electronic newspaper, but delicate structures nonetheless. So what we're thinking is, well, put one of our sheets in the back of it, give it some strength and stiffness, but at the same time not removing that rollability, that foldability, if you like, of the display, what it's offering, and at the same time offering protection to the structure.
You could basically have a computer screen, which was the size of a laptop screen, protected because it's got this nice strong back, it sits nice and flat, but when you click it, it will then roll up into something about 2 inches across. You put it in your pocket, but it's still quite protected because it's got this big metal sheet on the back and you can't crease it.
And so with applications like this, Keith, so e-book readers and electronic tablets, they're all very popular at the moment. And so in the future, we could just see thinner, more portable ones that would store quite neatly into our bags and be protected.
I think that's the sort of general aim where the industry might be heading. The thinner the display, the lighter it is, the less power it uses, but the more delicate it becomes. So you need some kind of protective backing on these, and one that enables or imparts the shape-changing capability that makes it easier to put in your pocket or wherever is something that would help.
Dr. Keith Steffen from the University of Cambridge. And Dave, although that roll-up computer tablet was just a mock-up, I could see how it could soon be possible, and it's now something I really want, given how much time I spend commuting on trains.
Yes, it was such a neat piece of engineering. Keith was taking something as simple as a bent piece of metal, understanding it on a very deep level, and then building such unlikely things, varying from flexible screen protectors for tablets or even rolled-up poles for the military.
And well, speaking of tablets, we now look at some engineering to do with the more commonly known form of tablet, and that's the drugs produced by pharmaceutical companies.
Tablet manufacture requires high levels of precision, working with a variety of chemical compounds to produce a wide range of very specific drugs. But more astonishingly, at a rate where tens of thousands or even hundreds of thousands of tablets are produced every hour.
Dave and I went along to the GlaxoSmithKline tablets manufacturing site in Ware, Hertfordshire, and met their Director of Innovation, Andy Robertson.
Where we make a wide range of drugs. We make drugs that people will recognise the diseases they treat. We make drugs for HIV and AIDS. We also do a lot of drugs for cancer. So we have a wide range of products with a wide range of applications.
So from the beginning, how are tablets made?
Well, this site at Ware is what we call a secondary process site. So what we do is we bring in raw materials, active ingredients, and we have to measure them out in the same and correct ratios to form the tablet.
So I guess if you've got lots of different ingredients in there, they must have different jobs.
What goes into the tablet really depends on the product, and each of the things going into the tablet have a different function. For example, you might require to put a bulking agent in there. So if the active ingredients is so strong, there wouldn't be enough to create a tablet. So you need a bulking agent to actually form the tablet. The other things that you might need is a binder to bind the powders together, as well as a disintegrant.
To help you absorb it once it's in your stomach or whatever, to let the tablet fall apart and so it is absorbed quick enough.
Once this is all together, what next?
Well, obviously, when they've been put all together in the correct ratio, we have to blend them to make sure they're all well mixed, so the blend becomes homogenized.
I guess this is a really critical step, because if it's badly mixed, you might get one tablet which is all filler and another tablet which is all active ingredient.
Absolutely.
But what kind of scales are we talking about here? We're in one of your control rooms now, and I can look out onto one of these large mixing bins. It's 1 metre wide and 1 metre high, so it's quite big.
Those bins hold up to 400 kilos. Just to put in context, those 400 kilos of bins, they can make up to 800,000 tablets.
One possible next step, having mixed together the ingredients, is granulation. So we're now in a large granulation room, standing by what looks like a hole in the ceiling out of which the ingredients actually drop into this processor.
Yeah, it is a bit like a food processor. So what you do is you put the contents of the bin into this food processor to change the properties of the material. So you're creating a granule and you're having to use a binding agent and water.
So instead of having a mixture of several different powders, you now have a load of granules. Each one is made up of all your different powders. This must stop the powders separating out in later parts of the process.
Absolutely right. That's one of the main reasons for doing it. This machine makes granules and then it discharges the granules through a wet mill, and the purpose of the wet mill is to chop them up into very small bits again before it drops into a fluid bed dryer. And the fluid bed dryer, you can see it's 4 meters high, it's around 1.5 meters in diameter. What that then does, it fluidizes the powder by passing air through it continuously. This is aiming to dry off excess water out of the granule, but not too much that it becomes a powder again.
Coming out of the bottom, then, I imagine, is the perfect formulation to then make a tablet.
It's nearly ready to be made into a tablet. Before we put it into a compression machine to make tablets, we add a lubrication substance called magsterate. This allows the tablet to be pressed out of the tablet after forming without breaking it.
Now, having gotten everything together, ingredients of the right consistency, it's now time, I guess, to make tablets.
Yes, this tablet press you see in front of us here is making around 40,000 tablets an hour.
I'm not surprised that it's making so many, because it's just whizzing, it's a cylinder whizzing around now, and I can just see hundreds of tablets in, the past minute that we've been here.
The way the tablet press works is a rotary die, which is a plate with loads of holes in it, with 2 punches, top and bottom punches. So as the plate goes round, the powder fills up all the holes, and the punches then compress it into a tablet and then punch those tablets out.
And you're measuring how much powder you got in there by basically, if it fills up the plate, then that's going to be a consistent volume every time.
That's right.
So now we have tablets and they've been checked that they are correct, but what next between here and actually sending them out?
So what we do before the tablets leave this facility, we then coat the tablets in a coating machine, and the coating process is rather like a tumble dryer where we're spraying liquid onto them and coating them slowly. And part of the reason for coating the tablet is to protect the ingredients from the environment, for example. It could also be masking any unpleasant taste when the patient takes the tablet, ease of swallowing the tablet, and it can even be used for improving the mechanical strength of the tablet.
I guess you can affect how it's dissolved, so you could put a coating on there which isn't dissolved in the acidic conditions of your stomach, so it can get through to the small intestines.
That's exactly right. And after the coating process, the next step after that is actually the packaging process. So they can either be packed in what we call blister packs, but they also can be packed into bottles.
We've now moved away from the actual manufacturing area on the site, but we've seen the ingredients being mixed, tablets being formed and coated. But Andy, how throughout this process are the tablets tested to actually make sure that they're all actually the same and uniform?
The quality assurance of the product is that each of the unit operations are fully understood and known, and all the critical parameters are monitored through the process. And during each of those stages, samples are taken and ensured the various test parameters are achieved, such as at the tablet press stage, we take the samples out and test for hardness, test for thickness, test for dissolution, and as a result, we know that the quality of the product is good at all points in time.
GlaxoSmithKline's Director of Innovation, Andy Robertson there, taking Dave and I on a tour of their tablet manufacturing site.
What struck me about this was their sheer attention to detail, as the processes need to be incredibly repeatable to ensure every tablet is exactly the same, so doctors can be confident that the tablet they're prescribing is what they think it is.
Laying the facts bare. The Naked Scientists.
You're listening to a special pre-recorded edition of The Naked Scientists with Mira Senthilingam and Dave Ansell.
This week we're discussing some of the highlights of our past year in engineering as we've travelled to numerous academic institutions and companies across the UK.
Now earlier we heard from friend of the show, Professor Hugh Hunt from the University of Cambridge, giving us an insight into the workings of the retroreflectors or cat's eyes we see lining our roads. But Hugh is a multi-talented engineer, and he's recently been involved in a project that looked into the engineering behind the famous Dam Busters bouncing bomb used during World War II.
And we joined him alongside the River Cam in Cambridge to find out what's involved in designing something on a large scale to bounce on water.
So Barnes Wallis in 1943 came up with this great scheme for blowing up German dams, having a bouncing bomb, bouncing on the water, nestling up against the dam, dropping down beside the dam to a depth of about 20 feet and then blowing up just at the right height. It was successful, although there were quite a lot of lives lost. But the technology was really quite fascinating and hasn't been reproduced since 1943.
Well, to find out more about the workings, I guess, of this bouncing bomb, we've come along to the River Cam. It's a beautiful sunny day. Dave, why are we here?
One of the things which inspired Barnes Wallis to design the bouncing bomb was essentially just skipping stones on a river. So normal skimming stones, you essentially get a nice flat stone, you get very, very low towards the water, and you attempt to throw it as hard as you can on a very, very flat trajectory, and with any luck, when it hits the water, it will skip.
Yep, so yours has just skipped twice over. It's actually quite hard to accomplish.
So what's happening is the stone hits the water at a slight angle. When it hits the water, it gains lots and lots of lift, and it bounces off, and it skips a few times.
And so, Hugh, is this basically the principles behind a bouncing bomb?
Barnes Wallis was sort of inspired by skimming stones, but actually he figured out with his kids in his back garden that he could actually get marbles, ordinary round glass marbles to bounce. The great thing about something round is that it can contain a reasonable volume. It is predictable, but actually there's an even better shape than being spherical. If you have something which is cylindrical, then you even fit more explosive power into the given space in the bomb bay of your Lancaster bomber.
And well, Hugh, this bouncing bomb is something that you set about recreating recently. So firstly, I guess, what do you even have to consider when designing or engineering a bouncing bomb?
First thing I suppose you have to do is to decide what size you're going to do it. Barnes Wallis had one which was about 1 metre and a bit in diameter. We went for half the size. Then we had to design how to fit it underneath a plane. We had to design how to make it spin, and that was one of the things that Barnes Wallis found was really important, that this thing had to spin. And we had to figure out how to release it at the right time, at the right height. And actually we had to make ourselves a target. And that was quite interesting because Barnes Wallis had German Nazi dams as the target. Well, we built our own dams.
Well, to see how you set about coming up with your design, and we've got a variety of bits and bobs around us. So we've got cricket balls here, we've got cylinders representing different scales of your bouncing bomb. So firstly, these cricket balls, what have you used these for?
Yeah, well, we started off on a small scale just with cricket balls. We used a cricket ball bowling machine in the Jesus Green swimming pool. And we wanted to figure out how we could make cricket balls bounce, and we worked out the height and the angle and the speed, and that was great.
So how fast were you actually having to fire these cricket balls to get them to bounce satisfactorily?
Well, the ordinary sort of lightweight ones, we could get them to bounce at maybe sort of 30 or 40 miles an hour. But the heavier ones, once we started putting weight in them, we had to get maybe up to 50 or 60 miles an hour, except if you put backspin on them. And this was a sort of eureka moment for Barnes Wallis back in the 1940s.
So why is backspin, I guess, so important, and how does it have a beneficial effect then to the movement?
Well, backspin is really important when the bomb goes through the air. Now, if you think of Roger Federer and his topspin makes the ball dip over the net really fast. So you can imagine put topspin on a spinning bomb, it would just dive into the water and just sink. But backspin, it sort of hovers over the net. And so you can make it skim at a much shallower angle onto the water.
So the important thing is the angle at which the bomb hits the water, and if that's too steep, it just digs straight in, but if you can get that shallow enough, it skips.
That's absolutely right, Dave, and if you have this thing called Magnus lift, the Magnus effect is what it's called, you can get a really nice sort of shallow angle onto the water. And we've got a really good demo of how that works.
So here to actually show us really just how important this is Hilary Costello, one of Hugh's PhD students. Now Hilary, you've got two polystyrene cups there that have both been taped together at their bottom ends, and then you have an elastic band which has been cut open.
Well, basically this is our cylinder or our bomb, is this sort of cylindrical polystyrene cup thing that we've stuck together. And then if you just wrap the string around, you can give it some either backspin or topspin depending on how you throw it. So if I just wrap the elastic band around the cylinder or the polystyrene cups.
Okay, so you've wrapped that round now, so there's not much elastic band left.
Yeah, and then if I just pull the elastic band with my thumb so that the cups go forward when I release it, it gives it some backspin, and you can see that it sort of hovers in the air before coming down.
So that actually hovered for about a good metre away from you.
Yeah.
Now you're just wrapping the elastic round again, but in the opposite direction so that you'll have topspin.
I actually just hold it from the top so that it has topspin. And then when I release it...
That pretty much went straight down to the floor.
Yeah, exactly. So the backspin gives it a little bit of lift and the topspin gives it a downwards force.
And Hugh, so why do we need this backspin and for it to hover, I guess, at quite a constant height?
Well, the idea really is to get the angle as shallow as possible. When you're skimming stones, we all know that you need to get down as low as you can, close to the water. But one of the problems that flying at night with gunfire and all this stuff, you really don't want to be flying very, very close to the water. So Barnes Wallis and his pilots really figured they couldn't fly lower than 60 feet. The backspin enabled them to get a shallower angle of bounce onto the water.
So this basically stabilises it, because otherwise after the first bounce it would start to tumble and it would go anywhere and stop skipping.
You've got a scaled model here, so it's a cylinder, it's got 180 millimetres, so 18 centimetre diameter.
Yeah, and this is what we used to do some tests. In fact, it was in the Cotswolds. We got a gas cannon to fire this cylinder at high speed across the lake, and we had to make it spin. And you can sort of see that, so if I toss this up in the air with no spin,
it's turned over, it's rotated.
Turned over very quickly. But once I put spin onto it,
it smoothly just comes straight back down to your hand.
It's the spin stabilised, and that was very important.
So what scales were you working to when you recreated your bouncing bomb?
So we've got the cricket balls here. We've got our 20 centimetre diameter scale model here. We've also got our 60 centimetre diameter bomb. It's actually a plastic replica because the real one was really heavy.
So you're going from lots of different scales. It's not entirely obvious that you can transfer things you've learnt on the size of a marble to the size of to something the size of a person. So was it easy to take information you'd learnt on the small scale to the larger scale?
Yeah, it's very interesting. Doing scale model tests, people designing aircraft do this all the time. They'll put a small scale model of an airplane in a wind tunnel, and they'll learn how the aircraft works at that scale, and then they'll scale it up to the big Airbus or Boeing full-size aircraft. And we did the same thing. We were able to use what's called dimensional analysis to scale up the effects that we saw at the small scale cricket balls up to the bigger scale.
So we've established, though, then that scaling is important and backspin is crucial. But what about, there are planes delivering these bombs, so there must be something about the speed they're moving, the height that the bomb's actually dropped at, and so on.
The critical parameters are speed of the plane, height that it's flying at, and how much you spin the bomb. And so for a given diameter, it turns out that if you do dimensional analysis, the speed squared divided by the diameter and g, the acceleration of gravity, is dimensionless. So that means that if you were to have a bomb which was twice as big, you would have to fly 40% faster, the square root of 2. And that's important to know that scaling factor.
And so moving back to you, Hilary, just to conclude, I guess, so having done all these tests with Hugh, what were your final parameters to actually drop the bomb and explode the dam?
Yeah, so from our testing, we determined that we needed to drop it 350 metres away from the dam, going 180 miles per hour, flying at 60 feet and spinning the bomb at 800 RPM. It turned out that on our final run, the pilot decided to fly a little bit lower at 30 feet, so the bomb did hit a bit harder than anticipated, but it was a successful run. So like Barnes-Wallis, we bounced a bomb and blew up a dam.
Hilary Costello, and before her Hugh Hunt from the University of Cambridge, taking us through the process of designing a large-scale bouncing bomb.
And now our final highlight from our year roaming the engineering world, and it's certainly a hot topic.
Yes, quite literally. Mira took Cambridge research student and metallurgist John Aveson along to the forge of blacksmith Gordon Bevan, where they watched him heat up and work a very tough piece of steel.
It was great, firstly, to see this process in action, as I hadn't seen it before, watching a tool such as a chisel form from a metal rod. But secondly, to actually know what was going on at the atomic level as this happened, as John explained.
Even though ironworking has been done for about 4,000 years now, it's only in the last 100 years or so that scientifically we've kind of understood exactly what's going on during all of the processes. So the art of the blacksmith is really to take a piece of metal and do a series of processes to it to give you the shape that you want, but also the properties that you want. And that really happens by controlling the structure really down to the atomic level.
So to see this in action, this week we've come along to meet Gordon Bevan, who's a blacksmith based in Eltisley in Cambridgeshire.
We make gates and railings, fire grates, anything to do with ironwork.
And well, today you're going to be making us a chisel. What are the main requirements of a chisel?
We're going to form the material into a chisel shape, and then we're going to harden it and then temper it.
So basically, once we've heated it, then it gets really easy to form into a certain shape that we want, because materials just tend to get softer the hotter they are.
Moving over to the forge now, what's the actual material burning underneath it? So what's the fuel?
It's coke.
Coke's just sort of coal that's been treated to remove things like sulphur. Putting a load of sulphur in the iron would be really, really bad news for the properties of the workpiece.
You've got a piece of metal heating up here in a bright orange flame, but what metal is this?
It's a piece of tool steel.
Tool steel is just an alloy of iron and carbon, fairly small amounts of carbon in there. What makes it particularly good is that if you keep carbon contents low in iron, then it's possible to harden it really, really well without having the sort of brittleness of cast irons and other sort of higher carbon content steels.
So Gordon is just pulling the metal out now, and the end of it is bright orange, so it's just burning hot. What temperature must it be reaching, John?
It must be about 900 Celsius, like really, really high temperatures.
And so what are you able to do with the metal at this high temperature, Gordon?
The oranger it is, or white, the softer it goes, so it's easier to hammer. Now when I hammer it, it's going to be easier to handle.
And John, what about the metal then makes it so extra kind of bendy and I guess malleable at such a high temperature?
Well, there's two things. Atoms are just moving around lots faster at high temperatures, so it's really easy to slide them past each other and permanently deform the material. But also, iron's got this really, really unique property that at about 700 Celsius, it transforms from being one crystal structure to another. And the higher temperature crystal structure is a lot easier to deform. So there's two real reasons why it's so good to work it so hot.
Hence why I guess when Gordon's hammering it into shape here, the end has become quite nice and flat and sharp now.
Yeah, exactly.
What's the next step? You've heated it and you have bashed it pretty much into the shape you want.
We're now going to harden it. We're going to quench it in some water.
So you're just dipping it into what just looks like it's a bit dirty water, it's a bit murky, it's brown, but it's not like it's even ice cold water, it's just simply room temperature water that you're dipping this into.
That's right. It's probably warmer than room temperature because it's standing by the forge.
So a minute ago this was reaching up to 1,000 degrees or something, and now you're just handling it.
It's now hard and cold.
So what has made it become hard simply by dipping it in this water, John?
Iron, and especially iron carbon alloys, have this remarkable thing that when you quench them down from really high temperatures, like 1,000 Celsius that we saw before, they form this crystal structure called martensite. It only happens when you cool things down really, really quickly. And this structure is really, really hard to deform, hard to bend, but it also is ridiculously brittle. So if you were to hammer it or to bend it or something, it would just shatter straight away.
So Gordon, you've made it malleable, bendy, and knocked it into shape, hardened it by dipping it in the water. What's next? It's starting to really look like a chisel.
I'm just going to clean it up now on linisher, sharpen the end, and then it'll be down to getting it hot again and tempering it.
You've placed it back into the forge now, and one of the reasons you've just cleaned it up is so you can see the colours at which it's burning.
That's right, so I can see the colours. It should go straw. If I go past straw, it will go to the blue, which will be too soft, so I need to stop it before it gets to the blue stage.
And this is all the end of the chisel, the bit that you've actually worked.
Yeah.
The fact there are different colours gives us like a natural thermometer to tell us, just by eye, how hot the steel is. We want to get a mixture between the hard, brittle martensite with the much softer but much more ductile and malleable low-temperature iron structure. Just by judging the temperature, we can choose the mixture that we get between those two different types of crystal. That locks in the final properties of the tool.
So as Gordon mentioned, he doesn't want it to get to the blue colouring, which is far too hot, and so is that therefore too malleable?
Yeah, that would end up too malleable. Too much of the martensite would disappear, and so it wouldn't be hard enough to be a really useful tool. It's this last step that really locks in the properties that give the tool what it needs to do its job.
So looking at it now, it's got that straw colour, which is what you wanted, but there is a bit of blue, and so you've pulled it out now. Is that now just to cool it down a bit to stop it being that blue?
Yeah, I'll stop it when the tip gets to the straw colour, like it's getting straw now. So now I've got to cool it off.
Interestingly, this time to cool it, you haven't dipped it into kind of room temperature water. You've dipped it into a box of oil.
Used oil. It's slightly better than water.
The oil will take the heat out of the tool a lot more slowly, and so we can really lock in the crystal structures that we put in by just picking the colours perfectly on the tool before we quenched it. It's a lot more gentle and it's a lot nicer process to the poor bit of metal.
Okay, so Gordon, you're just pulling that out now, and I don't really want to touch it. It is covered in oil.
Just got to be wiped off and then we'll try it. Yeah, it's cold now, so we can try it on the side of the anvil, see if it'll cut.
Is it any good?
It's not shattered and it's not dented, it's perfect.
So just using the skill of a blacksmith, Gordon's managed to control the atomic structure of a piece of iron to be able to cut another piece of metal perfectly. It's really, really amazing skills.
John Averson from the University of Cambridge, and with him blacksmith Gordon Bevan, who John and I joined at his metalworking site in Eltersley, Cambridgeshire.
This was an interview I've wanted to do for years. I've chatted to a variety of blacksmiths and they have a very intuitive feel for iron. But it's amazing how complex a material it is when you really get down to the science.
Yes, I have to admit, a lot more complex than I gave it credit for. Now, unfortunately, that's all we have time for this week. We hope you've enjoyed discovering some of our favourite pieces of engineering from the past year. My favourite of all of these was in fact the Blacksmiths, despite my overheating by that incredibly hot forge.
I'd say mine was a process for ore separation used in mining, because it was something I'd never even thought about. But in general, I just really enjoyed meeting all the engineers and spent far longer chatting to them than I probably should have done.
Yes, Dave, I definitely agree with that. Now, although that's it for this week's Highlights of Engineering, do join us again next week when Diana O'Carroll will be digging deep to bring you the best bits from the world of archaeology, including dating Neanderthals from the Mezmeskaya cave and the art of throwing a spear. In the meantime, you can see videos of all the pieces of engineering Dave and I have discussed this week online at thenakedscientists.com/engineering. And if you've got any questions for us, tweet them to @NakedScientists, write on our wall at thenakedscientists.com/Facebook, or email chris@thenakedscientists.com.
The Naked Scientists comes to you from Cambridge University and is supported by the Wellcome Trust, the EPSRC, the Natural Environment Research Council, and UK FAST. For more information, look us up online at thenakedscientists.com.